time we talked about density, and today we are going to apply that to the topic of pressure, specifically in fluids. So the pressure of anything is defined as the force per unit area. So if you have a really big force, but it's applied over a very large area, that's not very much pressure. You could also have a small force over a teeny tiny area that would be a lot of pressure. And pressure is a scalar. It does not have direction. It just is. The units of pressure that we are going to use in this class are called pascals, abbreviated PA. And 1 pascal is a Newton per square meter. It turns out anytime that an object is in a fluid, there is a pressure associated with that fluid. And the pressure at a certain depth, h is for height, the pressure at a depth h below the surface of a liquid is due to the weight of the liquid above it. And this is represented by the formula: pressure equals density times acceleration due to gravity times height. And you will need to use this equation, so you probably want to write it down somewhere. And this relation is valid for any liquid whose density does not change with depth. So anytime the density is uniform, you can use this equation. And the really cool thing is, it doesn't matter what the volume of the fluid is, only the depth. So if I were to sit at the bottom of a swimming pool and I wanted to know the amount of pressure acting on my body, I would take the density of water, which is 1,000 kilograms per cubic meter, multiply that by 9.8, and multiply by how deep I was in the pool. It doesn't matter if the pool is a mile wide and a mile long, or if it's 4 feet wide and 4 feet long. As long as the height of that water is the same, I will always feel the same amount of pressure on my body. So here's a quick example. The tanks in this picture are located 100 meters above a town and can hold water to a level of 30 meters. What is the water pressure at the town when the tanks are full? Well, we know that the pressure of a fluid is equal to density. Remember, this is our little symbol rho, times 9.8 times the height. So all we have to do is plug in our numbers. The density of water is 1,000 kilograms per cubic meter. Multiply that by 9.8. And the total height of the top of this water is going to be 130 meters, because these tanks are 100 meters above the town, but then the water inside them is also an additional 30. And when you do all that out, it turns out that the pressure in these water tanks is 1.27 times 10 to the 6 pascals, or 1.27 million pascals. That's a lot of pressure. When we talk about pressure, we also have something called atmospheric pressure. So the air around us is a fluid because it's a gas, and therefore it has pressure. At sea level, the atmospheric pressure, or the pressure that the air exerts on us, is about 1.013 times 10 to the 5 pascals. That's a lot. This is called 1 atmosphere. And we don't think of it as being a lot because we don't really feel this pressure, but it is a significant number of pascals. Another unit of pressure other than the atmosphere, which is abbreviated ATM, is called the bar. And 1 bar is 1 times 10 to the 5 pascals. Remember, a Newton per square meter is a pascal. So they all kind of equate to one another here. We have 1 atmosphere is approximately 1 bar, which is about 1 times 10 to the 5 pascals. And we also measure atmospheric pressure in millimeters of mercury. I'm not going to go into the conversion to that yet. We will talk about that in a later video. But let's think about this for a second. At sea level, which is about where we are, we have about 1 × 10⁵ pascals of pressure pushing on us at all times from every direction. So why doesn't it make us do something like this? One times 10⁵ Pascal seems like it would be a lot of pressure. Why don't we implode when we're down here? It's because the cells in our body maintain that pressure on the inside of our bodies as well. So if we were to take a look at our bodies, and I'm going to draw this weird, mushy, gingerbread man looking thing, we have about 1 atmosphere, or 1 × 10⁵ pascals of pressure pushing on us all the time from every direction because of all of the air that is above and around us. And the reason why we don't implode is because our cells are trained to maintain that pressure and push out an equal amount. Now, this is why, if you were to just go into outer space and jump out of the spaceship with no protective gear, you would probably explode. Because the cells in your body are maintaining about 1 atmosphere of pressure pushing out. And when you're in space, all of this pressure on the outside disappears. So then you have all this internal pressure pushing out and nothing to counteract it, and you would blow up like a balloon, and your blood would probably boil, and it would just be bad news. So most pressure gauges, or a dial, measure the pressure above atmospheric pressure. So if I had a pressure gauge to measure the pressure in a balloon, and I was measuring it right here in the classroom, it would tell me how much pressure that balloon has disregarding atmospheric pressure. And this is called the gauge pressure. But the absolute pressure is when you add the gauge pressure plus atmospheric pressure. So let's say my balloon had a pressure of 0.1 atmospheres. The gauge pressure would be 0.1, but the absolute pressure would be 0.1 plus 1 atmosphere of atmospheric pressure. So it would be 1.1. So your homework questions are, 1, how much pressure does a fire hose have if it can produce a spray with a force of 600 newtons, and the hose has a cross-sectional radius of 7 centimeters? That means if this is our hose, that radius right there is 7 centimeters. And what was the amount of pressure acting on James Cameron when he went to the bottom of the Mariana Trench, which he just recently did in 2012? And the Mariana Trench is 6.8 miles under the ocean surface. How much pressure was acting on him when he was down there? You may need to use our handy-dandy density chart here. So there it is as a reference.